In the name of Almighty God, I'm Mahsa Hassan Kashi, and today I want to talk about air and water purification in order to hinder contamination. Ventilation is crucial in energy efficient homes to maintain indoor air quality and comfort. There are two primary types of mechanical ventilation: spot or exhaust systems for specific rooms like kitchens and bathrooms, and whole house ventilation for the entire building. And the types of ventilation. The first one is spot ventilation, bathrooms and kitchens. This type use exhaust fans in bathrooms at least 50 cfm and range hoods in kitchen at least 100 cfm to remove moisture and odors. Make sure these fans vent air outside our home. And the whole house ventilation, why it's important. Natural ventilation often isn't enough for good indoor air quality. Whole house systems provide consistent and controlled ventilation throughout our home. And the different types. The first one is exhaust ventilation system. These systems remove air from house, creating a slight vacuum. They are simple and low cost but might not work well in humid areas and can draw in air from unwanted places. The next one is supplies ventilation systems. These systems bring fresh outdoor air into our home. They can work independently with their own ducts and or connect to your central air system. And about air purification. An air purifier or air cleaner is a device which removes contaminants from the air in a room to improve indoor air quality. These devices are commonly marketed to people with allergies or asthma and at reducing or eliminating secondhand tobacco smoke. The commercially graded air purifiers are manufactured as either small standalone units or larger units that can be affixed to an air handler unit or to an HVAC unit found in the medical, industrial, and commercial industries. Air purifiers may also be used in industry to remove impurities from air before processing. Pressure swing adsorbers or other adsorption techniques are typically used for this air purification. In 1830, a patent was awarded Charles Anthony Dean for a device comprising a copper helmet with an attached flexible collar and garment. A long leather house attached to the rear of the helmet was to be used to supply air, the original concept being that it would be pumped using a double blues, a short pipe allowed breeze air to escape. The garment was to be constructed from leather or airtight cloths secured by straps. In the 1860s, John Stenhouse filed two patents applying the absorbent properties of wood charcoal to air purification. Patent 19th July 1860 and 21st May 1867, thereby creating the first practical respirator. In 1871, the physicist John Tyndall wrote about his invention, fireman's respirators, as a result of a combination of protective features of the Stenhouse's respirator and other breathing devices. This invention was later described in 1875. In the 1950s, HEPA filters were commercialized as highly efficient air filters after being put to use in the 1940s in the United States Manhattan Project to control airborne radioactive contaminants. The first residential HEPA filter was reportedly sold in 1963 by brothers Manfred and Klaus Hammes in Germany, who created the Instant Air Corporation, which was the precursor to the IQ Air Corporation. What is the use and benefits of air purification? The first one is dust, pollen, pet dander, mold spores, and dust mite feces can act as allergens, triggering allergens in sensitive people. Smoke particles and volatile organic compounds can pose a risk to health. Exposure to various components such as uh, volatile organic compounds increases the likelihood of experiencing symptoms of sick building syndrome. Purifying techniques. There are two types of air purifying technologies: active and passive. Active air purifiers release negatively charged ions into the air, causing pollutants to stick to the surfaces. While passive air purifications units use air filters to remove pollutants. Passive purifiers are most efficient since all the dust and particulate matters is permanently removed from the air and collected in the filters. Several different processes of varying effectiveness can be used to purify air. As of 2005, the most common methods were high efficiency particulate air filters and ultraviolet germicidal irradiation. And about the filtration. Air filter purification traps airborne particles by size exclusion. Air is forced through a filter and particles are physically captured by the filter. Various filters exist, notably including high-efficiency particulate arrestants. Filters remove at least 99.97% of a 0.3 micrometer particles and are usually more effective at removing larger and smaller particles. HEPA purifiers, which filter all the air going into a clean room, must be arranged so that on air bypasses the HEPA filter in dusty environments. A HEPA filter may follow an easily cleaned conventional filter or pre-filters, which removes coarser impurities so that the HEPA filter needs cleaning or replacing less frequently. HEPA filters don't generate ozone or harmful byproducts in the course of operation. The next one is filter HVAC at MER 14 or above are rated to remove airborne particles of 0.3 micrometers or larger. A high efficiency MER 14 filter has a capture rate of at least 75% for particles between 0.3 and 1 micrometers. Although the capture rate of MER filter is lower than that of HEPA filter, a central air system can move significantly more air in the same period of time. Using a high-grade MER filter can be more effective than using a high-powered HEPA machine at a fraction of the initial capital expenditure. Unfortunately, most furnace filters are slid in place without the airtight seal, which allows air to pass around the filters. This problem is worse for the high-efficiency MER filter because of the increase in air resistance. Higher efficiency MER filters are usually denser and increase air resistance in their central system, requiring a greater air pressure drop and consequently increasing energy costs. There is ongoing research to enable viable and effective biocide-treated air filters, for example air filters coated with antimicrobial agents for preventing the spread of airborne pathogens. And what is the other method? The first one is ultraviolet germicidal irradiation (UVGI) can be used to sterilize air that passes UV lamps via forced air purification. Ultraviolet germicide radiation system can be freestanding unit with shielded UV lamps that use a fan to force air past the UV light. Other systems are installed in forced air systems so that the circulation for the premises move microorganisms past the lamps. Key to this form of sterilization is the placement of the UV lamps and a good filtration system to remove the dead microorganisms. For example, forced air system by design impede a line of sight, thus creating areas of the environment that will be shaded from the UV light. However, a UV lamp placed at the coils and drain pan of the cooling system will keep microorganisms from forming in these naturally damp places. The most effective method for treating the air rather than the coil is in line duct systems. These systems are placed in the center of the duct and parallel the airflow. The next uh, method is activated carbon. Activated carbon is a porous material that can absorb volatile chemical on a molecular basis, but doesn't remove larger particles. The adsorption process when using activated carbon must reach equilibrium, thus it may be difficult to completely remove contaminants. Activation carbon is merely a process of changing contaminants from a gaseous phase to a solid phase. When aggravated or disturbed, contaminants can be regenerated in indoor air sources. Activated carbon can be used at room temperature and has a long history of commercial use. It is normally used in conjunction with other filter technology, especially with HEPA. Other materials can also absorb chemical but at a higher cost. The next method is polarized media electronic air cleaners. Use active electronically enhanced media to combine elements of both electronic air cleaners and passive mechanical filters. Most polarized media electronic air cleaners use safe 24 volts DC voltage to establish the polarizing electric field. Most airborne particles have a charge and many are even bipolar. As airborne particles pass through the electric field, the polarized field reorient the particle to adhere to a disposable fiber media pad. Ultrafine particles that are not collected on their initial pass through the media pad are polarized and agglomerate to other particles, odor, and the VOC molecules, and are collected on subsequent passes. The collection efficiency varies significantly by particle size. The efficiency of polarized media electronic air cleaners increases as they load, providing high efficiency filtration with air resistance typically equal to or less than passive filters. Polarized media technology is non-ionizing, which means no ozone is produced. The next method is photocatalyst oxidation. Photocatalytic Photocatalytic oxidation is an emerging technology in the HVAC industry in addition to the prospect of indoor air quality benefits. It has the added potential for limiting the introduction of unconditional air to the building space, thereby presenting an opportunity to achieve energy saving over previous prescriptive design. As of May 2009, there was no more disputable concern raised by the Lawrence Berkeley National Laboratory data that PCO may significantly increase the amount of formal heat in real indoor environment. As with other advanced technologies, sound engineering principles and practices should be employed by the HVAC designer to ensure proper application of the technology. Photocatalytic oxidation systems are able to completely oxidize and degrade organic contaminants. For example, volatile organic compounds found low concentrations within a few hundred ppmv or less are the most likely to be completely oxidized. PCO uses short-wave ultraviolet light, commonly used for sterilization, to energize the catalyst, usually titanium dioxide, and oxidize bacteria and viruses. PCO in duct units can be mounted to an existing forced air HVAC system. PCO is not a filtering technology as it doesn't trap or remove particles. Like polarized electric media, the effectiveness of PCO approaches are highly dependent on particle size, and system geometries must be tailored accordingly. PCO systems are sometimes coupled with other filtering technologies for air purification, and ultraviolet sterilization bulbs must be replaced about once a year. Manufacturers may require periodic replacements as a condition of warranty. Photocatalytic oxidation system can often have high commercial costs. A related technology relevant to air purification is photoelectrochemical oxidation. Photoelectrochemical oxidation, while technically a type of PCO and PECO, involves electrochemical interactions among the catalyst material and reactive species. For example, to emplacement of cathodic material to improve quantum efficiency. In this way, it is possible to use lower energy ultraviolet radiation as the light source and yet achieve improved effectiveness. The next method is ionizer purifiers are usually charged electrical surfaces or needles to generate electrically charged air or gas ions. These ions attach to the airborne particles, which are then electrostatically attracted to a charged collected plate. This mechanism produces trace amounts of ozone and other oxidants as byproducts. Here we are to simulation with ANSYS Fluent. How simulation helps clean and manage water. After After the water goes down the drain, whether via home, commercial, or industrial uses, many of us forget about it. However, that water has a long way to go before it is put back into the environment. It is collected and sent to the wastewater treatment plants, where it is cleaned via chemical and mechanical processes before being discharged. Simulation is put to work in this phase of the urban water cycle as well. Wastewater treatment is closely regulated by stringent government standards and is essential for sustainable process. Indeed, industry leaders regard sustainability as a social responsibility, preventing pollution and reusing water as one of our most precious resources. The goal in such environmental initiatives is to extract waste materials as efficiently as possible by maximizing throughput rates using the least amount of energy. Simulation has been used to simulate many water clarification and also air purification process that enable designer to accommodate more stringent effluent quality limits and increase throughput. For example, engineers use ANSYS Fluent CFD solutions to help optimize water treatment by simulating a new dissolved air floating model in which injected air bubbles are used to transport solids in waters to the surface where they can be removed. Additionally, ANSYS simulation is used to visualize and predict how sediment settles in the bottom of tanks to maximize their efficiency. ANSYS fluid dynamic simulation has also been used to help design and operate WWT systems in chemical processing plants. This represents a huge step forward in an industry that has traditionally relied on replicating past design in the new plants. One example focuses on the critical steps in WWT operations in which screened and filtered liquid waste are treated in a large aeration basin, essentially a large tank with inlets for receiving raw material and an outlet for draining of treatment effluent. Naturally acclimated bacteria within the basin break down the organic compounds into the safe material. At the bottom of one of the basin lengths of pipe with small aspirating nozzles blow out air bubbles that transfer oxygen into the sludge to accelerate the composition of the waste. The composition process in another basin is aided by the stirring action of floating aerators, whose impellers push liquid waste together with oxygen bubbles downward toward the basin floor to discourage settling and promote a more even distribution of bacterial action throughout the mixture. Several variables, including gas, liquid fluid, turbulence, dissolved oxygen, and biochemical reaction kinetics, were combined into a large domain model consisting of 10 million computational cells representing the entire sludge basin. A subsequent comparison of the basin's dissolved oxygen measurements with fluid dynamic calculations showed good correlation, thus validating the accuracy of the approach. And this validation gave engineers confidence in using the model in a wide range of simulations that provided insight into design chains for optimizing the performance of the sludge basin. Using the CFD model, engineers could change a few key parameters to quickly study various alternative configurations in arriving at the most efficient design for meeting performance criteria. Many of simulations used Fluent to create user surfaces that define boundaries separating regions of various oxygen levels or liquid velocities. For example, such displays are helpful in understanding the characteristics of a complex system undergoing multiple behaviors, and how simulation helps manage water. While freshwater is only a very small percentage of Earth's overall water supply, it can still be too much of a good thing. ANSYS simulations are used to represent complex fluid structures, soil interactions to aid environmental risk assessments to prevent flooding, as well as improve water management by optimizing storm water systems, spillways, culverts, and dams. Runoff from sediment in stormwater contributes to polluted rivers, lakes, and basins. One customer employed anti-simulation to save weeks of design time and reduce the cost of physical prototyping by more than 80% by simulating a new design. Other customers use anti-fluent simulations to improve the internal hydrodynamics of water basins to mitigate pollutants in the rainfalls runoff and simulate water flow and turbulence in vegetated stormwater ponds, increasing their treatment capabilities. And CFT simulations have even been used to evaluate water conditions that are safe for fishways that enable fish like salmon and steelhead trout to migrate past dams. Power plants also use ANSYS simulation to evaluate the environmental impact of discharging cooling water from thermal and nuclear power plants into nearby water reservoirs, rivers, and lakes. Modeling and simulation of air-water upward annular flow characteristics in a vertical tube using CFD. Annular flow refers to a special type of two-phase flow pattern in which liquid flows as a thin film at a periphery of pipe, tube, or conduct, and gas with relatively high velocity flows at the center of the flow section. This gas includes dispersed liquid droplet. The liquid film flow rate continuously changes inside the tube due to the two-process entertainment and deposition. To determine the liquid hold-up, pressure drop, and the onset of dry-out and heat transfer characteristics in annual flow, it is important to have proper knowledge of flow characteristics, especially a better understanding of entrainment fraction is important for the heat transfer and safe operation of two-phase flow systems operating in an annular two-phase flow regime. Therefore, the objective of this work is to develop a computational model for the simulation of the annular two-phase flow regime and assess the various existence models for the entrainment rate. In this work, computational fluid dynamics or CFD in ANSYS Fluent has been applied to determine annular flow characteristics such as liquid film thickness, film velocity, entrainment rate, deposition rate, and entrainment fractions for various gas-liquid flow conditions in a vertical upward tube. The gas core with droplets was simulated using the discrete phase model or DPM, which is based on the Eulerian-Lagrangian approach. The Eulerian wall film model was utilized to simulate the liquid film on the tube wall. Three different models of entrainment rate were implemented and assessed to user-defined functions. in ANSYS. Finally, interment for fully developed flu was determined and compared with the experimental data available in the literature. From the simulations, it was obtained that the Berthoudin correlation performed best in predicting interment fraction and the results were between the positive negative 30% limit when compared to the experimental data. Here you see we have two systems, a CFX and also fully fluent. There are some different systems in the left side, and you can go through these tools and analyze systems and pick up one of them or some of them. And also there is a possibility that you can connect geometry from the CFX to the geometry from fluid flow. Uh, each system has a specific characteristics and a specific steps to go on and make a simulation. The first step in Fluid Fluent is to select geometry that we have selected the geometry such as this one. There is a room, a specific room, and we want to perform our air ventilation here. The next one is a mesh because we are using finite element method. uh, we need to have a very slice of this whole geometry, and we have to divide our geometry to the very small and tiny, especially when we are in a rounded on it's not in this solid surface. We have to reduce the size of the mesh, and this networking help us to integral the whole system from heat transfer or pollutant transfer. And the next is to go to setup. In the setup systems, we have to use models, and these models we can uh, check the energy on, and we have to use that if we are using a laminar flow or turbulence flow. In order to use a turbulence flow, we have to specify the specific and particular parameter as epsilon or omega. And after that we have to define a material. These materials we have to two different and two phase. The first one is the solid one, as a wooden or a steel, and the next one is our fluent material such as air or water. The next step is to define boundary conditions. The boundary conditions we want to use is that which section is our inlet and which section is our outlet. As you see that here there is a ventilator, and we can specify that here is inlet, and the door of the room is here after the corridor, and this is the our outlet. And after that we can specify our method as a spec, and also residual, and also initializing our simulation, and after that go to run calculation. In order to calculate our simulation, we need to define the number of iteration, and also reporting intervals. For example, uh, after each one step we can have a report, and after it's done we can go through the simulation, and you can see that how these pass lines go through the room and purify the air and eliminate air pollution and contamination from the space. Also, it can happen by the mentioned methods that I have described when I was reviewing the literatures that I have described, that how we can also have a water purification. We can have a inlet for injecting some sort of sterilizing chemical, for example, any sort of safe chemical, and from inlet, and we have purifier water or air at the outlet or the whole in our whole systems. Thank you so much for watching my video until the end, and also you can download these simulations from github.com/masterskill. And I have to explain that, for example, if I'm explaining and describing the ANSYS, there is a extension and you can find type ANSYS and file the different ANSYS projects from my GitHub.